Hey there, this is Bryan D. I'm here with my first AI homework, and let's just jump right into it. Okay, so first we see the main file, and this is just the .cpp file. This is the only .cpp file. All the rest are .h's. As we can see, all that happens in the main here is interface. We create an interface screen.start is called. So that is where all of the things are actually going to happen. So this is interface. And as we can see here, interface only has a default constructor. It's just set to default, and it only has one method. This method is start. This is our UI for the game, I guess, for the puzzle solver. And what it does is it takes in values for like your difficulty level. You can select easy, medium, hard, or custom. And then it does a switch statement for that. If it's custom, it runs through a loop to figure out what you want. And then we select the method, and then we get the method in. We go to a switch statement, and these are where the puzzle methods are called. So now let's go over to the solver.h file. These are where all of the solving methods are included. As we can see here, we have more to our class. We have all the search methods here, a destroy the nodes method, and a print method for printing out the search path. Let's go straight into breadth first search. Breadth first search uses a list of node pointers as a queue. It also uses a hash map of ints and bools. The int is set to the state value, which is the value of the array of the state, of the board state for a node. And then it sets a boolean, and the boolean is true if it's been used. The boolean is false if it's not. Okay, so on in breadth first search, it's a little different. I only use one hash map because, well, it's just kind of easier, and you only have to loop through one thing, or you only have to check one thing. So I figure if you find something and on one level, the cost is going to be cheaper than if you find it on another level. Plus, you're not checking for cost and breadth. Duh. But so what happens is you go while true, some bookkeeping here, and then here is where we get our first test. If pointer misplaced equals 0. Pointer is set to, at the very start, it's set to the start node, or a pointer to the start node. And we should go into node class now and look at this. So the node has a bunch of different bookkeeping things. And what it starts off as here, crap. Okay. So misplace is the number of misplaced tiles. And if that is equal to 0, then we break out of this loop and we have found our solution. And the solution gets passed to the print method. Yeah. So if we haven't found that and we continue on, we call the children method in the node. And what this is this method, this big switch statement here. And what this does is it takes, I modeled the 8 puzzle in an array. And what it does, and I did this just simply for like visual. So if it measures where 0 is, and then based on where 0 is, it changes the values. It swaps the values in states for all the possible like children boards that you could go to here. So here we see it's creating a new array. This array switches from the state 3 to state 0, and state 0 to state 3. And then what it does is it pushes back, it pushes a new node, well, a pointer to the new node, onto the vector of kids, which is a vector of pointer nodes, or yeah, of node pointers. And then it breaks out. And then it doesn't return anything, it just ends. If we go back into solver, so now after we've gotten that, we loop through all of the children by going x equals less than kids.size. We get the next kid, and we set it to a pointer. And then we check the kid to see if it's in the used hash map. If it is not in the used hash map, then what we do is we insert the state value into the used hash map as the key, and then set that boolean to true. And then line dot pushback is just push it to the back of the queue. And then we pop off the front of the queue and we go again. And yeah, this works pretty well. Then we call the printer method to print it out. Let's go to depth first search. So depth first search I did pretty differently. The queue actually isn't a queue. I utilize the parent-child relationship. And what I do is I go all the way down the parent-child depth until I hit either depth 32, which is one move over the maximum amount of moves that a puzzle needs to solve itself. So I know that there's a solution above depth 32. This was an optimization thing. You can take it out right here, but and it will just work off of the used. So what this does is search is set to false if we loop back all the way up to the very parent node, and if it finds the state value equals one of its parent's node state value, it calls off the search and it heads back to its parent node down here while destroying the child node because we don't need it anymore. It also adds to kids visited plus plus, or kids visited plus plus, so that we can go to the next node in that parent's kids. Now we'll go down to A star. We create a struct for A star for priority queue. I skipped all of these because they're exactly like A star, except for the only difference is this struct. This is how the priority queue organizes itself. So we create the struct A2 compare, we put it into the priority queue, and then we go. We also have a hash map here for this is a node pointer hash map, so it has so it's able to actually interact with the pointers or with the actual nodes. So what this does is so if we find that a child state value has been in used and the child state value is less than the one already in used, which could also be in the queue. Well, actually, no, it can't be in the queue because if that parent one, the state value is in used and it's already been visited here, then this will go false and push will equal to false, and we won't push the child in. Otherwise, it will set the previous node that was pushed into the queue visited equal to true, and if it's equal to true, then it won't interact with anything in here. We won't get any childs from it, and we'll just skip on to the next one. Yeah, and then we set the node to visited equals true, so we don't so we know that it's off the queue. We pop it off the queue, add to the stack, and set the pointer on the new top. I guess I'll go show print method here real quick. So what this does is it takes in a node pointer and it creates a stack. What it does is it runs all the way up to the very parent node, pushing the pointer onto the stack, or the new node pointer onto the stack. And then we go to while directions not empty, print out start, and then pretty much print out the rest of the things. Here is where we print out the actual board. We divide the X by modulo 2 to create like an actual board look, and then we destroy the nodes here. So let's look into the code real quick. So we'll go straight to hard because that'll show that it actually works on all of them. So it works on all of these search methods. Let's go to search hard, and there we go. We did the A star 2 method on the hard search, and we found all of the moves. And then at the bottom it prints off the cost. Okay, I'm trying to wrap this up so it doesn't go over 5 minutes. Thanks for watching.